Dear learner, I will explain chemical bonding of senior secondary stage. Objectives of this program is to explain the formation of bonds in terms of potential energy diagram, and I also discuss octet rule. I will discuss the different types of bonds, ionic with examples, similarly covalent with examples and their characteristics. I will explain Bonhoeffer cycle, then I will discuss BSEPR theory, hybridization, and finally molecular orbital theory. Now first question arises, what is a chemical bond? When two atoms of same or different elements approach each other, the energy of the combination of the two atoms becomes less than the sum of energies of the two separate atoms at a large distance. The bond is called chemical bond. There are different types of chemical bonds such as ionic or electrovalent, covalent bond, coordinate covalent bond. In addition to these, we have a special kind of bond called hydrogen bond. If you take the example of sodium chloride, according to causal theory, there is a transfer of one electron from sodium atom to chlorine atom, and both the atoms attain noble gas configuration. The positively charged sodium ion and negatively charged chloride ion are held together by electrostatic attraction. The bond so formed is called an electrovalent or an ionic compound. Thus, the ionic bond can be visualized as the electrostatic force of attraction that holds the cation and anion together. The compounds so formed are termed as ionic or electrovalent compounds. Energetics of the ionic compound formation. You may raise a question here that when more energy required to ionization enthalpy to form a sodium ion from sodium atom than that released electron gain enthalpy in the formation of chloride ion from chlorine atom, then how do we say that the formation of NaCl is accompanied by the decrease in energy? This can be explained on the basis of Bonhoeffer cycle. The formation of sodium chloride from sodium and chlorine can be broken down into a number of steps. First stage, sublimation of solid sodium to gaseous sodium atoms. Na solid to convert into Na gaseous state, delta H will be 108.7 kilojoule per mole. Ionization enthalpy, that is, you can say sodium gaseous state, liberate one electron, delta H will be equal to 493 kilojoule per mole. In all both the cases, you will find energy will be absorbed. Dissociation energy of gaseous chlorine molecule into chlorine atom. Half chlorine gas coming to Cl gas, delta H will be 120.9. All these values are positive because energy is absorbed. Now, you will find here that now chlorine gas is converted into chloride ion, energy is released here. So, you can simply say that is minus 379.5 kilojoule per mole. Formation of sodium chloride from sodium and chloride ion, that is called crystal or lattice energy, lattice formation. You will get Na plus gaseous state, Cl minus gaseous state to give Na plus Cl minus solid. Delta H will be negative, that is minus 754.8 kilojoule per mole. The energy released in this step is lattice energy. The net reaction would be Na solid plus Cl2 gas to give Na plus Cl minus solid. Delta H will be minus 410.9 kilojoule per mole. The overall energy change can be computed by taking the sum of all the energy changes, that is minus 410.9 kilojoule per mole. That is called heat of formation. So, if the heat of formation is negative, then compound will form. If it comes positive, then compound will not form. Now, you can see the Bonhoeffer cycle in the diagram form, where you can say that Na solid plus half Cl gas, delta H, that is Na plus Cl, that is called heat of formation, that is solid. So, you can see the 5 steps are there: heat of sublimation, ionization enthalpy, dissociation energy, electron gain enthalpy, and finally lattice energy. On the basis of above discussion, we can say that the formation of ionic compounds is favored by number 1, low ionization enthalpy of the metal, 2, high electron gain enthalpy of the other element, that is non-metal, and high lattice energy. Now, characteristics of ionic compounds, we can say these exist as crystalline solid in which the ions are arranged in a regular three-dimensional structure. The ionic compounds are generally hard and brittle in nature. These compounds have high melting and boiling points due to strong electrostatic interaction between the ions. Now, they are less soluble in non-polar solvents but more soluble in polar solvents. So, you can say that ionic compounds are soluble in water but insoluble in alcohol, ether, etc. These compounds conduct electricity when in molten state or in aqueous solution. Causal theory explains bonding quite well, but only for a small class of solids composed of electropositive elements of group 1 and group 2 with highly electronegative elements of group 17. Secondly, this theory is incapable of explaining the formation of molecules like SO2 or O2, etc. For example, in case of O2, there is no reason to expect the one atom of oxygen would lose 2 electrons while the other accept them. The problem was solved by Lewis' theory of covalent bonding. Now, I will discuss the covalent bond. Lewis assumed that atoms attain noble gas electronic configuration in the process of bond formation. However, the way the noble gas electronic configuration is achieved is different. Lewis proposed that this is achieved by sharing of a pair of electrons between the two atoms. For example, two hydrogen atoms chemical bonding form a molecule by sharing a pair of electrons. If electrons are indicated as dots, the formation of hydrogen molecule can be explained over here. You will find here H, one electron, plus another H, other electrons. Since they are homonuclear molecule, so position of pair of electron will remain between them. You will get H single bond H. This shared pair of electrons contributes towards the stability of both the atoms and is said to be responsible for bonding between the two atoms. Such a bond is called covalent bond, and the compounds so obtained are called covalent compounds. Now, another category of bonds is coordinate covalent bond. In some cases, both the electrons of the shared pair are contributed by only one species, atom, molecule or ion. A common example is the formation of a bond between boron trifluoride BF3 and ammonia. You will find nitrogen donate a lone pair electron to BF3 to give NH3 BF3 addition compounds. Bond polarity and dipole moment, this is the most important. A covalent bond is formed by sharing of a pair of electrons by two atoms, each one of which contributes one electron. If the two atoms have same electronegativity, then the sharing of two bonded atoms is equal, as I told you just now in case of hydrogen. Such a bond is pure covalent and it is non-polar in nature. So, H2 molecule form a bond which is non-polar in nature. However, if electronegativity of two bonded atoms are different, as in hydrochloric acid, HCl, then the shared pair of electrons lies more towards more electronegative atoms, that is chlorine. As a result, a small negative charge delta -1 develops on chloride ion Cl atom and an equal positive charge develops on hydrogen atom. The covalent bond in hydrochloric acid is a polar covalent bond. So, we can explain here that polar and non-polar covalent bond, if molecules are homonuclear, that is hydrogen, chlorine, atom, molecules, etc., that will be non-polar. But if we take HCl, HF, etc., then bonding will be polar. Dipole moment is the magnitude of charge into distance of separation. It is commonly measured in unit d by symbol capital D. The SI unit of dipole moment is coulomb meter. The two units are related to H. 1D is equal to 3.36 into 10 to the power minus 30 centimeter. Now, here you will find that the dipole moment of some molecules, bond, electronegativity of hydrogen atoms, then dipole moment HF, HCl, HBr and HI. Now, we can also explain that dipole moment is a vector quantity since it has direction and magnitude both. By convention, the symbol this is used to represent the dipole moment. For example, carbon dioxide molecule is a linear triatomic molecule. Each C double bond O bond is polar and the oxygen atom having the negative end of the bond dipole. You will see here that since both the bond dipole are opposite to each other, so carbon dioxide will not show net dipole moment. So dipole moment of carbon dioxide will be 0. The dipole moment of both the CO bonds having the same magnitude but are in opposite directions, hence they cancel each other. The net dipole moment of CO2 is 0. Now ammonia, most interesting example here. NH3 has a pyramidal structure which makes the arrangement of 3 NH bonds unsymmetrical. In each NH bond, nitrogen is negative center and hydrogen is the positive center. You will see the diagram. Now in case of ammonia, ammonia has a pyramidal structure which makes the arrangement of 3 NH bonds unsymmetrical. In each NH bond, nitrogen is a negative center and hydrogen is a positive center. So since it has one lone pair of electrons, so magnitude of dipole will be in opposite direction. So we'll find here, since there are 3 hydrogens, so net ammonia will show dipole moment. Fajan proposed some empirical rules that deals with the polarization process. These rules are known as Fajan's rules. The following factors increase the covalent character of an ionic bond: a small cation, large anion, high positive charge on the cation. Covalent parameters. The bond order is the number of bonds present between 2 atoms in a molecule or ion. Generally, bond order has an integer value. Now, bond order is 1, which there is only one covalent bond, sigma bond, between H2, Cl2, ammonia, or some example are given over here. Now, similarly, you can take bond order 2, oxygen, oxygen, or ethene. Bond order 3, you can take acetylene or nitrogen. Bond length. Bond length is the distance between the nuclei of the 2 bonded atoms. It is expressed in picometer, that is pm. Bond length depends upon the size of the bonded atoms and the bond order of the bond linking them. The greater the bond order, smaller is the bond length. Bond HH, HF, HCl, HBr, HI are given over here, that is 74, 92, 127, 141 and 160. Now bond angle, it is the angle between the 2 bonds in a molecule. Since covalent bonds are formed through overlapping of orbitals, it may also be defined as the angle between the 2 orbitals that contain bonding electrons and overlap with other orbitals of other atoms. You can see the picture here. That is the bond enthalpy. It is the amount of energy required for breaking one mole of bonds of a particular type in gaseous molecule. It is also called bond dissociation enthalpy and is applicable to simple molecule containing only one bond of the particular type. Now, the another category of bond, which is also known as hydrogen bond. It is the special type of attraction between a hydrogen atom bonded to a strongly electronegative atom, say nitrogen, oxygen or fluorine, and the unshared pair of electrons on another electronegative atom. Hydrogen bond is a weak bond, the strength being just about 4 to 5 kilojoule per mole. Now, in fact, it is due to the hydrogen bonding only that water exists as a liquid. The low density of ice can also be explained in terms of hydrogen bonding. So, we will see hydrogen bonding in water. Similarly, you can explain hydrogen bonding in ammonia HF molecule. There are 2 types of hydrogen bonds. If the hydrogen bond is formed between the 2 different molecules, it is called intermolecular hydrogen bond. For example, we can say here water, HF and ammonia. When the hydrogen bond exists within the same molecule, it is called intramolecular hydrogen bond. Intramolecular hydrogen bonding exists in orthonitrophenol and salicylaldehyde. Now, valence shell electron pair repulsion theory. This theory has 2 main postulates. Number 1, the electron pair, both bonding and non-bonding around the central atom in a molecule, arrange themselves in a space in such a way that they minimize their mutual repulsion. In other words, the chemical bonds in the molecule will be energetically most stable when they are as far apart from each other as possible. For example, BF3, the central atom boron has an electronic configuration 1s2, 2s2, 2p1. That is, it has 3 electrons in its valence shell. In this process of covalent bond formation with 3 fluorine atoms, 3 more electrons are contributed to the valence shell. Thus, there are a total of 6 valence electrons of 3 pairs of valence electrons. According to BSA-PR postulates, these electron pair would try to keep as far apart as possible. It makes the 3 electron pair to be located at an angle of 120 degree, which gives the molecule a planar trigonal shape. Now, some examples are given in this table. Now, another postulate 2H, chemical bonding, the repulsion of a lone pair of electrons for another lone pair is greater than that between a bond pair and lone pair, which in turn is greater than between the 2 bond pairs. The order of repulsive force between different possibilities is as under. You will find here lone pair repulsion is more as compared to lone pair bond pair is more as compared to bond pair. I will take one example. For example of methane, ammonia and water. All the 3 contain a total of 4 electron pairs around their central atom. But the nature of these is different in the 3 cases. In methane molecule, the central carbon atom has 4 valence electrons and it shares 4 electrons with 4 hydrogen atoms. So, there are a total of 4 bond pairs. However, in ammonia, you will find here 3 bond pair and 1 lone pair. And in water, 2 lone pair and 2 bond pair. Now, we can explain modern theories of chemical bonding. After the development of quantum mechanical description of atomic structure, 2 more theories were proposed to explain the bonding between the atoms. These are called modern theories of chemical bonding. These are number 1, valence bond theory, commonly known as BBT, and molecular orbital theory, commonly known as MOT. Now, valence bond theory proposed by Hitler in London in 1927 to describe the formation of hydrogen molecule from its atom. Linus Pauling and others further developed it. In this approach, the process of chemical bond formation can be visualized as the overlapping of atomic orbitals of 2 atoms as they approach to each other. The strength of bond depends on the effectiveness or extent of overlapping. Greater the overlapping of the orbitals, stronger is the bond formed. Let us take the example of bonding in hydrogen molecule to understand the BB approach. You will see here diagram is given here. You can explain in terms of diagram. Hybridization is the process of forming a new orbitals by mixing of atomic orbitals in a particular atom. The new hybrid orbitals that are formed are all equivalent orbitals and have the same energy. The phenomena is known as hybridization. 2 main characteristics of hybridizations are: the number of hybrid orbitals formed is the same as the number of atomic orbitals undergoing hybridization. All the new hybrid orbitals that are formed are exactly identical in their shapes and energy. Example of bonding in triatom molecules in beryllium. Now, picture is given over here that first you will find 1s2, 2s2, then 1 electron is excited, 2p. You will find here that 2 hydrogen overlap with the 2s and 2p. Now, the 2 valence electrons are in 2 singly occupied orbitals which can overlap with the 1s orbitals of the 2 hydrogen atoms and form 2 bonds. The problem is solved with the help of a concept called hybridization of orbitals. According to this, 2 or more than 2 non-equivalent orbitals having different energies and shapes of comparable energies mix or hybridize and give rise to an equal number of equivalent same energy and shape hybrid orbitals. In the case of BCl2, the 2 singly occupied orbitals 2s and 2p hybridize to give 2 sp hybrid orbitals. This is called hybridization. These hybrid orbitals lie along the z direction and point in opposite directions. Now come to the resonance. Sometimes it is possible to write more than one Lewis structure of a compound that agree with the electronic configuration. We can write 2 Lewis structure for ozone molecule. Now I will discuss here in some detail. See the structure of ozone. Ozone has 1 double bond and 1 single bond. So 2 bond lengths should be different, but it has been found that both the bond lengths are same. It means it has 2 resonating structures, so no bond is double, no single bond. It always have bond order, that is 1.5. So you can say all the bond order are same. So bond length will also be the same. So you can explain resonance structure of carbon dioxide, sulfate, etc. Similarly, we can, as I told you, we can explain the structure, resonating structure of carbonate. It has 3 resonating structures. Now we will discuss molecular orbital theory. Molecular orbital theory, that is MOT, was developed by F. Hunds and R. S. Mulliken in 1932. It describes bond formation as a result of overlapping of the atomic orbitals belonging to the constituent atoms. The overlapping region responsible for bonding is situated between the 2 atoms. It is localized. According to MOT, in the process of bond formation, the atomic orbitals of the constituent atoms combine to generate new types of orbitals called molecular orbitals. These molecular orbitals are created by linear combination of atomic orbitals, that is LCAO, approach in which the atomic orbitals of comparable energies and of suitable symmetry combine to give rise an equal number of molecular orbitals. The available electrons then fill these electrons in order of increasing energy, as in the Auer principle used in the electronic configuration of atoms. Now here you can see the hydrogen molecule. Now in case of hydrogen, 1s1 is the electronic configurations. So 2 atoms of N1s1 combine together. Since the electrons enter into the sigma 1s bonding molecular orbitals, so we can calculate bond order will be equal to half number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals. Since in case of S2 molecule, both the electrons are present in bonding molecular orbitals, so S2 molecule will have single bond order, that is bond order is 1. So S2 will exist. However, if we explain the existence of He2 molecule, you will find that He2 molecule will not exist, because in case of He2 molecule, there are 1s2, so 4 electrons are there. So 4s2 will go into bonding molecular orbitals. Now He2 molecule, you will see here the electronic configuration 1s2. So there are 2 H molecule, H atom combined together to form He2 molecule. So there are 4 electrons, 2 will go into bonding molecular orbitals and 2 will go into anti-bonding molecular orbitals. So if you calculate bond order 2 minus 2, it will be 0. So we can say He2 molecule will not exist. So you will find this question can be asked in the examination also. The molecular orbitals obtained by the addition of atomic orbitals is of lower energy than that of atomic orbitals are called bonding orbitals. On the other hand, the orbitals obtained by subtraction of atomic orbitals is of high energy and is called anti-bonding molecular orbitals. The molecular orbitals obtained here are symmetric around the bond axis, the line joining the 2 nuclei. Such molecular orbitals are called sigma molecular orbitals. The bonding orbital obtained above is denoted as sigma 1s, while anti-bonding orbital is denoted by sigma anti-bonding 1s. Here sigma indicates the type of molecular orbital, 1s tells about the atomic orbital involved, and star is indicative of the anti-bonding nature of molecular orbital. We write MO electronic configuration for molecule. The MO configuration of hydrogen molecule is given as 1s1 bonding molecular orbital. Now there 2 pictures are given over here. You can see hydrogen molecule is given, He2 molecule is also given, as I have already discussed to you people. Bond order I have already discussed. We may define a new parameter called bond order. Bond order, that is half Nb minus Na, where Nb and Na refer to the number of electrons present in the bonding and anti-bonding molecular orbitals respectively. For hydrogen molecule, the bond order will be 1. There is a single bond between 2 hydrogen atoms. Now these diagrams are given for fluorine and oxygen molecule. You will find here the fluorine H, you will find that is 9 electrons and oxygen has 8 electrons. It means the total 16 electrons, and fluorine has 9 plus 9, 18 electrons. You can subtract the 4 electrons because 1s will not take part in the bonding. So oxygen will have 12 electrons to be accumulated here, and fluorine has 18 minus 4, that is 14 electron. We have to fill up sigma 1s, you can leave it, sigma 2s anti-bonding, then sigma 2p, then pi 2py is equal to pi 2z, then again pi 2py is equal to pi 2z, then sigma 2px. You can fill up this. In the case of oxygen, it has 2 unpaired electrons. Therefore, oxygen molecule is paramagnetic, whereas fluorine molecule is diamagnetic in nature. Now, in case of nitrogen molecule, an atom of nitrogen has 5 valence electrons. Since there are 2 atoms, we have a total number of 10 valence electrons that need to be filled in the molecular orbitals. The molecular orbital electron configuration can be written as sigma 2s2, sigma antibonding 2s2, pi 2pz2, pi 2py2, pi 2px2. Bond order will be half Nb minus Na, that is 8 minus 2, this will be 3. This means that in nitrogen molecule has a triple bond exists between the 2 nitrogen atoms. This means that in the nitrogen molecule, a triple bond exists between the 2 nitrogen atoms. Magnetic nature, as I have already told you, molecules magnetic behavior depending on their molecular electronic configuration. If all the molecular orbitals are doubly occupied, the substance shows diamagnetic behavior. In case of one or more molecular orbitals are singly occupied, the substance shows paramagnetic behavior. So, molecular orbital diagram of oxygen I have already told you, with 12 electrons, valence electrons are 12, you fill up sigma 2s2, sigma antibonding 2s2, sigma 2pz2, pi 2p y is equal to pi 2px2 to each, then pi antibonding pi 2px1. Since it contains unpaired electrons, oxygen shows paramagnetic behavior. Thank you.